I'm John Stalcup. This is Roberto Lublinerman. We are software engineers at Google, and we work on the GWT compiler. It is our only responsibility, and kind of our goal is to make it much, much faster. Historically, it's been, in our opinion, a little bit slow, and we have a lot of ideas in the short term and in the long term for how to make it faster. I'm going to talk about our short-term ideas, which are focused mostly on faster draft compiles, and Roberto is going to be talking about our longer-term ideas, which are a little bit harder to pull off, doing local and global optimizations in parallel ways. So just a little bit of a review before I get into our plans for how to make draft compiles faster. Kind of want to set the stage for how are compiles performing right now. So I'm going to tab over to, have you guys seen this application before? You probably have. This is the Showcase widget gallery app. It's a sample that ships with the GWT SDK. It exercises just about every widget in the standard toolkit. So it's not a small application, but it's also not a giant application. It's like a medium-sized application. So I'm going to use this as kind of a performance comparison test bed for how are compiles performing right now. Someone can. It's a good idea.
Except that the camera won't see you anymore, so the recording won't be so good. So there are scenes here, so I don't know. Just guess.
Use binary search.
If you turn off the lights, then we can control the camera because we don't.
Even if it's a little. That's a good compromise. Can you record there? Or?
Can you see that fine?
Yeah.
Okay, cool. Okay, so I'm going to go over some of the compile performances with different sets of flags and different cache levels for the Showcase application. So, now I'm in the other slides. Okay, so as a developer, when you're wanting to get fast turnaround, you turn off all the different permutations because it takes forever to compile 6 or 30 permutations depending on what your settings are. So the first step is turn off all your permutations. And with this application, if you're compiling just one permutation, the performance comes out on this laptop at about 63 seconds, which is kind of slow. That's really not how much time you want to be spending waiting around every time you make a change. There's kind of a breakdown of where that time is being spent. I'm going to go into those details a little bit more a little later. So the second time you compile, you're actually going to get a little bit faster performance. So what's going on there is under the covers, the compiler has a cache of what we call compilation unit. And it's basically, there's one compilation unit per Java source file. And if some of those compilation units haven't changed, we can actually take the cached serialized version off disk and reload it really quickly. So what you're seeing in the first row is on the second compile, we went from spending 20 seconds in JDT compile time. That's where the JDT compiler takes Java source and translates it into a naive Java AST. And those 19 seconds, or 19 of those 20 seconds went away. So that's that's a good gain. We're happy with that. But we also lost a little bit of time over here in the kind of unmeasured other area because it takes time to interact with this unit cache. But on the whole, we gained, 17 seconds or something, 16 seconds. So when you want to get it even faster, you play with your flags a little bit and you turn on draft compiles or optimize 0, basically. They're mostly synonymous. And you can see we get the compilation performance down to 37 seconds, which is better. It's significantly better. And you can see we've got a pretty significant gain, mostly in the normalization and optimization phase. So we turned on draft compile flags, and as a result, instead of doing a full global optimize, we did just a really quick optimize. But you may notice we're still spending 17 seconds on what's supposed to be a minor optimization. A lot of that's because of semantic normalization that has to occur. So this is kind of the state of the world right now, and it's not a great state. So what do we do to maintain developer productivity? Well, we provide SuperDev Mode, or Dev Mode, regular Dev Mode and SuperDev Mode. So everyone is probably pretty familiar with the regular Dev Mode. It's a Java-based hosting environment. And the changed refresh time there is pretty good. If you make a change, refresh in the browser, it cycles pretty quickly. But there are some downsides. The initial browser connection time, especially in Chrome, but also somewhat in Firefox, can be pretty long. It can be as long as a regular compile. So you start questioning how much you're really gaining. You also need to relaunch it every now and then. And it can hide some minor bugs. So it's not the best situation. But really, the biggest strike against it is the fact that browser support for the API necessary to be able to provide dev mode is going away pretty soon in both Firefox and Chrome. So we have to think about what we're going to do in the future. So the future is mostly about SuperDev Mode. SuperDev Mode is not a behind-the-scenes kind of fake Java hosting environment. It doesn't require any sort of hidden proprietary plugins for browsers. It's a real true-to-life JavaScript compiled experience. But the downside with it is it doesn't really perform quite as well as regular dev mode. And you have to wonder, why is that? Well, the reason is SuperDev Mode really amounts to a wrapper around a warm draft compile. So there's no magic there. A warm draft compile takes 37 seconds in this example. SuperDev Mode is going to take about 37 seconds in this example. So if we want to make the world better for GWT developers going forward to SuperDev Mode, we need to make draft compiles significantly faster. So that's what we're focusing on in the short term. So you have to, we asked ourselves the question, why is the draft configuration still slow? Why is it that when we turn off all the permutations, we have a warm cache, we turn off all the optimizations, we're still spending 37 seconds compiling? Well, the first thing we look at is JDT is actually recompiling just the changed file, which is kind of what you want. Let's say we change one file, we recompile. JDT is only recompiling that one file, so that's pretty good. But the rest of the pipeline is actually processing all the files in the application. So the showcase application contains about 200 Java source files, and it depends on the GWT standard user library, which contains about 2,800 Java source files. So when you do this compile, if you change one file, one CSS file or anything, and you recompile, most of the pipeline is actually processing 3,000 files. And that's basically where the performance is going. We're deserializing 3,000 cached units. We're resolving references among them. We're normalizing the semantic behavior. We're doing a very minor optimize on all those 3,000 files, the AST representing those 3,000 files. And we output JavaScript source code representing all 3,000 of those files. So it basically is a design that doesn't scale very well. I'm sure everyone in the room has worked on a lot of different GWT applications, some large, some small. And you've probably noticed your large GWT applications just take progressively longer and longer to compile. And this is the root cause. This is the reason that occurs. So we asked ourselves, can we do better than this? Can we make the compile scale, the amount of time it takes to compile, be a direct reflection of the amount of files that have changed or the amount of change that's occurred? So the answer in a nutshell is basically yes. There are just several hurdles, several things that have to change to make it possible, but we've been working on those things. Basically, even in the draft compile, there are some global optimizations that occur, and global optimizations require global knowledge. So we've taken time to turn off all the global optimizations, at least for a particular type of compile. Sort of the API and the expectations that generators run in results in generator output only being accurate when they have access to global information, both for binding property configurations and what types are available and that sort of thing. So there are a lot of different reasons, and we don't have to get into all the technical details, but we've largely solved most of these issues. So I want to give you a demo of what it looks like with what we're calling separate compilation or library-based partial compilation. So here's the showcase application, and this is what I'm going to be recompiling. And over here in the Finder, here's a library where I have a collection of a whole lot of libraries that I've compiled that make up the showcase application. You can see this largest one down here at the bottom is the user library. It's the standard user library that comes with GWT. But there's also lots of different libraries, smaller pieces that make up the showcase application. I'm going to clear this cache of precompiled libraries, and I'm going to start up a separate compilation process from scratch. So basically what I'm starting up is a small build system. We don't actually have Buck or Gradle integration or a real build system that knows how to process GWT XML files and take advantage of parallelism and small chunks and partial compiles. So this is sort of a straw man build system, not for production use. But basically, you point it at a root library that represents an application. Here's the reference to the client interface for Showcase. And it walks the graph, and it collects all the different libraries seen from there, all the different GWT.xml files. So this is what it's seeing. It's asking me if I want to rebuild, so I'm going to tell it, go ahead and rebuild. And basically, it understands the tree structure, and it starts with leaf nodes. You need to compile the libraries at the leaves first. That makes it possible to compile libraries further up the tree because they take as input dependencies the libraries further down the tree that have already been compiled. So the user library is kind of massive. It's 2,800 files, so this one takes a while. This one takes about 60 seconds, actually. But the important point to note is basically each one of these libraries, when their output, is marked with a timestamp that represents the highest modification time of any of the files that they represent. So if any file that is a part of any of these libraries changes, the build system will see that and on the next invocation rebuild just that changed library. So it's minimizing the amount of work. Only the changed parts are recompiled, and then after the changed parts are recompiled, there's just a simple link process at the end. And the reason the link process at the end is fast as well is that it's literally a blind concatenation of the JavaScript output of all the other libraries. There's no global analysis. So this should be coming up in a second. There it is. OK, so the user library took 69 seconds to compile. These other libraries are much smaller. You see they're ticking off in less than 1 second, 2 seconds, a handful of seconds each. I'll go over to the directory. You can see them popping in. So imagine you've got a build system set up for your department. You've got like a shared directory where everyone who's using this build system is getting cache hits for their output. So most of the time, you're not going to see a full build. You're just going to, when you invoke build, you're only going to have changes, like small changes being recompiled. So it's going to be done in a second. There's a couple more. While it's chugging away, I'll talk about another point. So some people in the room probably remember GWT files, .gwtar. So those kind of promised the idea of libraries and separate compilation, but there was really a design flaw with GWTars. And the problem there was they weren't actually caching any of the work that was sort of involved in all the pipeline of the GWT compiler. If you look at the slides, switch over. You see where when you have a warm cache, your JWT compile time comes down from 20 seconds to 1 second. That's exactly the moment when GWTar files were being used. GWTar files contain pre-compiled individual compilation units that feed into this first caching layer. So the maximum impact that GWTar files can possibly have is to transition you from a cold compile to a warm compile. So that's why it's a completely different solution to the problem. So, I'm sorry. OK, so it's completed compiling all the different libraries. I can see them sitting here in this directory. And it actually also performed a link at the root. So I'm going to refresh in Firefox. And the size of the output JavaScript is actually a little bit large, so it takes Firefox a second to chug through it. The first time, it just needs to warm up. OK, there we go. OK, so if you're familiar with dev mode, you're probably familiar with the fact that when you click around in dev mode, everything is sluggish. It feels like kind of moving through molasses. This is real JavaScript just sitting in the browser, runs full speed. There's no back and forth with any hosted environment. So all this is just true to life browser performance. If I go over here and I make one change to one file, I'm going to make one change to one file. I'm going to tell the build system, recompile, find changes, recompile the minimal set. I'm going to refresh in Firefox, and we'll see how fast that occurs. So I'm going to change the size of the header from 20 point to 30 point. Save that and hit enter. So OK, so it sees that only the input to the client root library changed. It's recompiling. And this first recompile will probably take about 14 seconds. Oh no, it's less than 12. So it fluctuates. This is it's actually a 4-year-old laptop. It has severe garbage collection fluctuation issues. So that took 11 to 12 seconds, a refresh in Firefox, and I see my CSS change. So, yeah. Thank you. So my desktop machine is not 4 years old, and it's 3 times faster. So that changes 4 seconds on my desktop machine at work, which I think is approaching a pretty reasonable development experience. Stepping a little bit further, catch back up demo. Okay, so looking at this chart again, now with precompiled library support, how does performance compare? Well, in the final column, we see it's about 12 seconds after you make a change. And it depends on how small the particular library that you changed is. Like some may be longer than that, some may be faster than that. And it depends on your hardware, of course, too. But there's a lot of ways you can optimize this still. And so I'm going to get into some of those changes. But a point I want to make here is the GWT compiler for years, we look at all these stages. There's JDD compilation. There's reference resolution amongst all these units. There's optimization and normalization. There's all these different stages in the compiler. And for years, people have been squeezing on these stages, trying to make them as fast as possible, given the same amount of input. But it's kind of the wrong solution to the problem. Really, you can't make those stages much faster. You really need to provide them less input so there's just less work for them to do. And that's what libraries do. We got decreases, kind of dramatic decreases in time across all the stages because there's just less input for them to process. Yeah, they're synonymous, exactly. Yeah, they're one for one. Yeah, and the libraries, I can get into this a little bit, but there's basically a zip file that contains cache pre-compilation units as well as output JavaScript that represents that particular set of files that represents that module. That way, at the end, you can just concatenate these JavaScript files together. Yes. Yes, exactly. Yeah. So that's something I was going to get into. It's a great question. Basically, in the past, people didn't have very many knobs to turn. Once you're, I'm sorry. Okay, so he was saying that, I don't know if I'm going to phrase it properly, but he says that it's pretty normal practice to highly modularize your project anyway. And isn't that an advantage for this situation where you're going to be getting one precompiled library for each module? And that's exactly right. That is good practice, and that good practice will help your compile time. Sorry. Taking advantage of libraries. The original project structure before I modularized it actually only had one GWT XML file at the root, and it depended on a couple of different pieces from the standard library. So if I had tried to separately compile this, I wouldn't have gotten too much gain. I get some gain, but not too much. But looking at the folder structure, it was actually highly modularized. It just didn't have XML files all over the place. So I added one to each directory, set up a source glob for just the Java in that directory, and I was almost done. There were a couple of circular references I needed to break. There were some messages files in the root of the directory tree and some messages files in the widgets further down the leaf nodes of the directory tree that were referencing each other. So I pulled those pieces out, stuck them into a side directory, defined them as their own module. No more circular reference problem, and now you're back to your libraries being a tree that can be compiled. There's multiple ways to solve circular references. You can also introduce a common interface amongst the different code that knows about each other. So I introduced lots of modules to split up the work. Just in general, when you're doing this, you want to try to focus on making a tree that is shallow and broad, because the broader it is, the more parallelism there is available. So here's how it came out looking. Now, if I was using a real build system, not this sort of straw man I threw together, if I was using Buck or Gradle or one of these new up-and-coming efficient parallelized caching build systems, I don't just get recompilation of just my changes and relinking. I actually get parallelism as well. So you see this column of widgets here in the middle? These don't depend on each other. And it's completely possible to compile each one of these precompiled libraries in parallel. So if I change 3 or 4 of these, I can be running those on different machines or different cores, and I'm not paying the cost. It's a critical path analysis in the graph at that point. So there's a lot of advantages. And another advantage is, in the past, once your application got large, you were just sort of stuck with long compile times. But here, if you notice that there's one particular module or a set of modules that are slowing you down, you can just split them into smaller pieces, and you're no longer paying that whole compile cost. Briefly, I want to cover the sort of the options we're looking at. To really help developers and community take advantage of this, we need to make it easy. So we need to either build support for this into SuperDev Mode, or we need to have SuperDev Mode talk to one of these existing efficient build systems like Buck or Gradle. So there's trade-offs. Buck is kind of, I think it's faster, but it doesn't provide custom rule type support, so it's going to be harder to integrate. Gradle imposes some limitations on project structure, but does have custom rule type support. We're going to be looking at these issues, maybe working with volunteers in the community to make it happen, and talking to those build systems probably from SuperDev Mode. Technical details, I just wanted to cover a couple things before I hand it off to Roberto. While doing this work, we discovered that there's even more headroom left than we were kind of aware of. If you look at the number of compilation units that we process in our pipeline when we're doing separate compilation, let's say we're compiling classes A, B, and C. We're going to need to load up those classes, but we also load up classes referred to by those classes because we have to verify the correctness of references and super type hierarchy, that sort of thing. But when we log the types that we're loading in 2.5 times as many types as the JDT compiler does when it does pure Java compilation, which means that our lazy loading of references is overly broad, and that work is costing us time. The existing Java serialization method we use, it's costing us about 2 to 4 milliseconds per unit, which is kind of atrociously high. We need to do some work there. There's also a problem where when we load these cached units off disk, we deserialize them, we start processing them, our pipeline is actually modifying them. They're not immutable. And that means that once they're modified, if we want to use them again later, we have to deserialize them again to get a fresh copy. So wasting time there. Also, our reference resolution process potentially could be multi-threaded. Module XML parsing is costing a shocking half a second just to parse all the XML files involved. We think we've made pretty significant progress, but we think that there's still a lot more progress we could make. Roberto.
Okay, so I'm going to build up on what John was talking about. And I want to, we have approached this problem of making the compiler faster. And one question that you may have is that why is the compiler so slow with big applications? So if you look at the compiler, it's basically a pipeline. So it first gets all its source files, its Java files, pushes it through the precompile phase, gets a whole program AST. So at that moment, you have all the classes in a single internal representation, which you compile, you get JavaScript for, and then you bundle it together into jars. And it's basically a very sequential process in the current version of the compiler, and that's why we are trying to make it parallel. So the first phase, it's basically reading the module files, which are very verbose, and they're not cached, so they're reading all the files to find out which are the Java sources that you need to compile. Start to produce compilation units, which are basically internal representation for each Java class. And from that, we might discover that we need to run some generators. We run some generators, produce more code, compile that code, and keep on building all these small trees for each class. Then there's all stitched together into a big, giant AST. And here's when the fun begins. So basically, one of the main driving forces of building the compiler, I believe, I joined the team pretty late, but I believe it's to minimize the size. So this in 2006, the smaller you can get your JavaScript, it would make really, really a difference. So let's invest in time in compiling these applications, which were not as large back then as they're now. and do the maximum possible. And the only way to do the maximum possible is to know the whole program structure, so you can just get rid of methods that are not used, classes that are not used, fields that are not used, which you cannot do when you look at a single piece of a single class or a single module. So easy way to do that is, well, you build the whole tree for the internal representation, and you start doing passes on top of that. So you do some passes that eliminate these patches. You do some inlining to, when you do inlining as a side effect, you might get dead code removal, and you go on, and you loop over the passes until basically there's nothing left to do. And the compiler has managed to reduce your Java size to a much smaller than the sum of all these Java sources. And then the process begins to get it to be executable in the browser as JavaScript. So the first pass is, once you get the full Java source, then you want to simplify so that the translator is simpler. So basically, for example, if you have many catch blocks, you collapse them into one. So for things like longs that we want to preserve Java semantics, at that moment, all long operations and long variables are replaced by an emulation layer in Java. And the normalization also does global computations. For example, it finds out what are possible casts between objects and just records that, so that to have the minimal code to perform casts. And then we go and translate it into JavaScript. And that's the only happening in the compile phase. And once you have the JavaScript, because our source Java is a mixture of Java and JavaScript by Gisni, so we need to do some other optimizations to make the code even smaller. So we do some dead code elimination there, and we inline, and we remove unused functions, and we do other optimizations. And once that process is done, if people used run async is when the process of code splitting happens. And that also may be time consuming because the compiler basically traces all the chain of calls from all the run async points to see which ones can be split out from the main program. And once that is done, there comes a links phase where you combine all the output JavaScript from all the permutations and all the resources into jar files, and that's the output of the compile. So, so where is the time spent in a compile? So if you take a big compile, so this may vary depending on your application. But if you take a big application, basically link time is practically free. It's very small percentage of the time, and most time is divided into compile and pre-compile. So if we want to make the compiler faster, we have to focus on the pre-compile and compile phase and make those faster. So let's say we go and we did profile those passes on several applications, and this is a sample of one of the profiles. In this example compilation, there is the first bar is a precompile. It's a single precompile, produces the code for all the permutations. And then in parallel, there are three compilations. These are the next three bars, and there at the end, there's the link phase. And if you see, there are a lot of little pieces of color in at least in the precompile, and these are different little phases that happen there. For example, the green one is basically the compilation by JDT, and some of the red ones are generators. So you see, if you want to speed up that pass, you need to speed up basically every single part of it, most of it. In the compile phase, if you this big compile phase, the first the gray is the Java optimization phase, and the more purple grayish is the JavaScript optimization phase. And these take the bunch of the actual compilation, and the yellow is the code splitting. So if you just focus on making optimizations for performance, then you will reduce the total time by a small amount. So let's say you cut optimization by half, which is a ridiculously high goal. You wouldn't affect much your actual performance. So this problem needs to be rethought. And as John said, it's not just making each pass faster, it's making each pass do less with less data. So as we already seen, the idea is to compile modules separately, produce libraries. When you compile a module, you don't need to know anything, all the contents of the library upon which it depends. You just need to load some a small portion of the data to be able to compile a module. So the modules contain also the JavaScript output. So you run the whole compile pipeline on a very small piece of Java code, and you get the output. And then at the end, for draft compile, this will be the picture. You get the trees of modules. There is some dependencies. So some parts can be done in parallel. Some have to wait. What's important is the critical path. But the link phase will only needs to take just the output JavaScript for each module and do minimal concatenation processing and produce the output jar. So the question that gets raised is, how do we speed up the optimized builds? Because I think it's most important to do the draft build because it's the heavy development cycle. But if you get a big application and you get a optimized build that takes like maybe 15 minutes and you build 200 permutations, so you can imagine the time and resources that are invested in just compiling one application. So the idea is to leverage this compilation into libraries to extract. So when you compile a module into a library, you extract some little piece of information about the module, for example, classes that are present, methods that are present, and you build a small summary which you can then combine. You combine the summaries for all the libraries and compute some global knowledge about the program. You don't do anything about here you still don't have a big AST. You're not looking at the internal representation. You just work on a summary, and you compute basically the most important computation that you. So there are two things that you want to know. You want to know the whole set of classes that are in the program, and you want to know when you get any variable reference field, what's the actual type of the objects that end up there, because that lets you turn dynamic dispatch into static dispatch, and that lets you prune a lot of code. So the small global analysis phase will take all these summaries and compute and do the analysis there, type the variable, type the parameters there. And then once that's done, you have an optimization phase that runs independently in each module, for each module with the information that was computed in the global analysis. And this can be repeated. So once you optimize all the modules, you can produce new information, do a small sequential phase, and again, do that a couple of times. So in our current compiler, which we have such a loop, but it's not, it's all on the whole representation, we normally do like 11, 12 rounds of optimization until there's nothing to be gained. And almost like the first few 5 or 6 get you like 80% of all the whole improvement in size. So you can imagine that we can do this cycle for 3 or 4 times maybe and get the good results. And that's how it would look like the diagram of the compiler. So we would compile each of the modules separately. You produce a library. It has JavaScript output for draft mode. It has summaries for optimized compiles. If you're doing an optimized compile, then you will have global analysis, produce some information that can be used for the modules. It's also interesting to know that each module may not need the whole global information. It may need some just projection that for the things that you reference in it can be useful for compiling that module. You optimize that module, collect summaries again, and do a few times, and then result JavaScript, you link it together and output it in an application jar. So that's the plan that we're working on for getting the optimized compiles faster. And I have a wish list of what I would like to do. So the compiler has grown very complex. And so we have 2 representations that we currently need. because we cannot do optimizations in both of them. We cannot do all optimizations in one. For example, we have this Java representation that has also a little bit of JavaScript, so we don't know how to optimize that in the Java phase. So longer-term plan will be to unify into a single representation in which the compiler does all the optimizations. And the other big part is to, most of the optimizations now are done by traveling the whole tree. So here they will be done in modules, but actually it should be done in a kind of a data flow manner, in the sense that you do some work, discover what else needs to be done, and just add that to your work queue instead of traversing the tree over and over to find opportunities. And we have to rethink inlining. So inlining for code size is not very effective. So it's only effective if it's a getter or if it's a function that's called once. But inliner is an enabler. Inlining lets you discover that some conditions hold true, and you can and some paths are never taken, so they can be removed. So in the sense that we have to basically summarize the functions that are called and use the information, but not actually inline them. So in that sense, you could have all the benefits with none of the cost, let's say. And that's about it.
Thank you.